go over the solutions quickly. Okay, so for the first problem, mainly what we're looking for is for you to show some energy band bending in the gate, right? A little bit of depletion in the gate near the gate oxide. So that's for 1 point. And then for the remaining point of this problem, because the applied gate voltage is the same, so the difference between the Fermi levels in the gate and the silicon are the same. So if you introduce a voltage drop in the silicon, this band bending, then the voltage drops in the oxide and if you introduce a voltage drop in the polysilicon gate, then that means the voltage drops in the oxide and the silicon body have to reduce. So just qualitatively, you just have to show less voltage drop in the oxide in the semiconductor. And so since you have less band bending in the semiconductor, that means you need to apply more voltage to invert the surface. So the threshold voltage goes up due to gate depletion. For the inversion layer thickness, it's only relevant in the inversion regime of the CV characteristic. And as you apply more and more gate voltage, stronger and stronger into inversion, the inversion layer gets closer and closer to the gate oxide interface. So the impact of the inversion layer thickness decreases as you increase the gate voltage. Okay, so just qualitatively, you just had to draw a line below the ideal capacitance in the inversion regime and show that it's sloped upwards. Positive fixed charge, if you have positive charge in the gate dielectric interface, then that'll make it easier to invert the surface, so that'll lower the threshold voltage if this is an N-type transistor or NMOS device. And to increase the threshold voltage, you need to make the substrate more P-type, harder to invert, so you implant boron. Okay? Any questions on the first question? All right. MOSFET operation is just very qualitative. As long as, so the trade-off for threshold voltage basically is between high-speed circuit operation and low power. So as long as you said there's a trade-off between speed and power consumption, you get full points. Okay, so high speed means low VT, but low power means high VT. So that's a trade-off for selecting VT, and you'll get experience doing that in your design project. The second part of the MOSFET qualitative question was, okay, explain why as you increase the drain voltage, the on-current saturates. So as long as you say something about that the voltage that you can apply across the inversion layer is limited, because right? Basically, eventually, if you increase the drain voltage too much, you'll pinch off the channel. So that limits the total amount of voltage you can apply across the inversion layer to induce higher and higher drift velocity. That's basically the answer. Okay? Any questions or alternative ways to explain your answers for the second problem? Yes? Okay, so you said it's what? Turn off? Swapped. Okay. Okay. Well, we'll take a close look, just to see if you have some consistency in your answer. You can at least get partial credit for sure. Yes, Bjorn? Okay. So if you include the accumulation thickness layer, so that's fine. That's fine. Because yeah, the accumulation layer also has a thickness effect. So it will, again, so you start out with a line that's below the ideal, and it'll approach the ideal as you go to more and more negative voltage. So that's fine. You won't get penalized for that. Yes, Andrew.
I don't know if it's but for part B, I thought for part BI.
BI here?
Yeah, I. So.
Oh, here.
So I thought it was a depletion line instead of a poly.
Oh, you answered it thinking it's the thickness of the inversion layer. I mean, thickness of the depletion layer.
Yeah, because I thought it was respected for A.
Okay, maybe you explain to me after class, like what you were thinking. Okay. All right, any other interpretations? Okay. All right, for the second problem, the last problem, it's a little bit of calculation, but hopefully the arithmetic wasn't too complicated. But basically, you just have to recognize that this is a long channel device, so the voltage at which the current saturates is just VG minus VT, corrected by the factor M. So that's 1 volt. So you just have to set that quantity to 1, and I gave you VG, and I gave you M. So threshold voltage is 0.3, and then you just have to calculate, it's on this plot, actually the formula, right, VGS plus VT plus 0.2, it turns out to be a round number, 2, divided by 6 times the TOX equivalent, which is very close to 20. So basically, the numbers came out pretty round. So you just have to look at the mobility at 1 megavolt per centimeter, and it's roughly 250 centimeters per volt second. And of course, if you get something within some reasonable close value to 250, you'll get full points. Okay, it's not about accuracy here.
If you made an error in A and you propagate it all the way through,
Yeah, well, we will not take off. We will not penalize you for the same wrong answer all the way through. Yeah, don't worry. On-state resistance, this is from homework. As long as you plugged in the values for mu effective appropriately. VG minus VT is 1.2. So 1.2 times, well, anyway, it comes out fairly round, 1 over 3 kilo ohms. So 330 ohms. Like I said, as long as you're within 100% or something, you'll get full points. Okay, saturation current is just plugging in numbers, but hopefully you notice that VG minus VT is 1.2, and you have a 1.2 down here, so it cancels out, and you get a nice, relatively easy to calculate number. And finally, transconductance. Again, numbers are pretty round, but you have to use the formula, for the saturation regime of operation. Okay, and finally, showing the impact of channel length modulation. You just have to draw a line, showing that if you pinch off the channel and the channel inversion layer gets shorter and shorter as you increase the VDS, the drift velocity goes up because the lateral electric field goes up, so the current goes up. Yes, Bjorn? Oh, okay, yeah, so the question is, yeah, instead of Siemens, sure, amps per volt. That's the same as Siemens. Okay, so how do you think you did? All right? The last problem? You mean the channel length modulation? Okay. Now for the final, oh yes, Haley.
Well, I don't know, I might turn on
That's right, 1 over ohms. Siemens, 1 over ohms, amps per volt, yes, they're all the same. Yeah. Great, so for the final quiz, so I wanted to mention, because I do need to quiz you like one more time. So in 2 weeks on Tuesday, that's the Tuesday after Thanksgiving, you're going to have the final quiz. And in order to be able to test you on some stuff that I cover, I have to give you a short homework assignment that's due before that. Okay, so you only have 2 problems for homework number 13. It's due next Tuesday. Okay, so it shouldn't take much time. And then the final homework set, homework 14, will be due on the last Thursday, which is December 5th. But it'll also only be 2 problems. Okay, so you're not going to have, it's essentially like spreading out 1 homework assignment over the next 2 weeks. But I just need to be able to quiz you on something, right, for quiz 6. So the material of quiz 6 will just be the short channel MOSFET and just fundamental BJT operation. And that'll be it. So hopefully you'll have plenty of time to work on the project and get that done without having to pull an all-nighter, I hope. Okay, all right. So for the rest of this class today, it's just going to be kind of like a seminar. Usually the material I covered today is what I cover on the very last day of class. But since we're covering short channel MOSFETs, I figured we should just cover this material today, bring you up to speed on state-of-the-art CMOS technology. And then for the last 4 lectures of the class, we'll just cover the bipolar junction transistor, which actually is inherently part of the MOSFET, right? From the source to the body to the drain is NPN or PNP BJT. So I should mention, just to let you know, the next lecture will be rather short because that lecture will just introduce basics of bipolar junction transistors. But at the end of the class, we will have the HKN course survey, just to let you know. Okay? So I'd like to encourage you all to stay around to submit your course evaluations, because that's important for the university to see. Okay, so today is more like a seminar, and I brought some little models here. I don't know if any of you noticed this stuff in my office, but that's a model of the 3-dimensional transistor that I'll pass around, and the regular MOSFET that you've been studying. Okay, So because you're from, you're Berkeley students, so you really should know that 3D transistors were invented or developed here at UC Berkeley. I, together with Professor Chen-Ming Hu and Professor Boker and myself, our students basically were the ones who developed this technology more than a dozen years ago. And it was introduced in the most advanced microprocessor chips by Intel last year. Okay, but Intel actually made a big deal. There's a big press release in 2001. Intel bragging that it's introduced a really radical change in CMOS technology, the most radical change in 50 years. This is like an example of how to market your work, raise the stock price. So they call it a three-dimensional transistor design, which will enable lower power operation, either faster or lower power. So this all relates to VT. Okay, it turns out that the three-dimensional transistor, the FinFET, which most of the world calls the FinFET, it allows you to have a lower VT, but still have good low leakage current. So if you have lower leakage current, you have low power consumption. But if you have low VT with low leakage, then you can also have higher speed performance, right? So basically, what Intel calls a tri-gate transistor, or a three-dimensional transistor, is basically, essentially, the FinFET that was developed here at UC Berkeley in the late 1990s and early 2000s. So that's the topic of today. Okay, so we'll get to there. Okay, so first of all, in the late 1990s, the industry was manufacturing CMOS chips with a minimum gate length. The generation of technology is quarter micron. So on the order of 250 nanometers was the gate length, LG here. And we knew that following Moore's law, in about 10 or 15, within 15 years, we would need to manufacture transistors with gate length 25 nanometers. In other words, we could project at a standard pace of scaling that eventually we would like to make transistors with gate lengths as short as 25 nanometers. Now, in those days, people had tried to make the conventional MOSFETs with such short gate lengths, but then the leakage current was really high, right? Short channel effect was bad. Drain-induced barrier lowering was bad. So a lot of challenges, okay? So the primary challenge at that time, in the late 1990s, was getting the transistor to turn off properly, because the gate was no longer able to turn off the transistor with a high drain to source voltage, okay? So what we realized at Berkeley was, well, okay, when a transistor is turned off, in other words, with 0 volts on the gate, actually the leakage current that flows between the source and drain primarily happens away from the channel surface, okay? Actually, right at the gate oxide surface, the gate actually couples pretty well to the channel potential. So really, what we need to do to suppress leakage is just to physically eliminate all possible leakage paths between the source and the drain. So that's the idea of a thin body transistor. And actually, if you can rely on a very thin, if this body is thin enough, you don't even need to dope the channel to suppress the leakage. To get this high, source potential barrier height. You can actually even eliminate dopants in the channel. You don't need high doping to prevent the depletion region, from penetrating from the drain to the source, right? That Dibble effect. And that's actually good for enhancing mobility, so enhancing on-state current. Now, the easiest way back in those days to manufacture a thin body transistor was to start with a silicon on insulator substrate. So in other words, there are companies today that can manufacture single crystalline silicon on oxide, silicon dioxide, on top of another silicon wafer. So the way they do this is they take a silicon wafer with oxidized surface, and then take another silicon wafer and bond it face down. Okay, and then they etch away, they remove like the silicon wafer which was face down, and they can thin it down. It's a little expensive. So these silicon on insulator wafers are actually 10%, a few $100s more per 300 millimeter wafer than a bulk silicon wafer. So there's some cost involved. But in any case, the easiest way to make a thin body transistor is to start with a silicon on insulator wafer. And so researchers here at Berkeley and other places in the world started looking at ultra-thin body transistors. So the question is, how thin does that body have to be to suppress the leakage adequately? Well, it turns out that it really should be less than 1/4 of the gate length if you really want to suppress the off-state leakage pretty well. And so the thickness of the silicon layer, as I said, has to be much thinner than the gate length. Okay, so has anybody are you familiar with the International Technology Roadmap for semiconductors? There's a roadmap that the semiconductor industry sets for itself to scale CMOS, and they sort of project, okay, what kind of technology capabilities are going to be needed down the road so equipment companies can develop the processes in advance. So according to the roadmap, which is always 15 years from the present, what is the minimum gate length? I mean, what do you think is the ultimate, at the, quote, end of the current roadmap, what is the gate length? Today is the gate length is about 35 nanometers. 30. 10? You think it's 10? Okay, so let's say it's 10. Let's say we'd like to scale the gate length down to 10 nanometers. How thick does that mean that the body must be to suppress leakage? 2.5? Okay, so what happens with silicon, if you make it physically that thin, you get quantum confinement effects. So it's like you have a buried oxide underneath and a gate oxide on top. So it's like a high band gap materials sandwiching a small band gap material. So you basically have a quantum well for electrons and holes in the silicon. And so you start to see quantum confinement effects become significant if the body is actually thinned below 5 or 4 nanometers. Okay? Now what happens then is that the quantum confinement effect limits the energy, the density of states in the conduction band and valence band edge. So you actually have to apply more gate voltage to get a lot of carriers forming in the channel, inversion layer. So essentially it increases threshold voltage, okay, if you have quantum confinement. And what's worse is that if you have variations, this quantum confinement is quite sensitive to the thickness of the silicon. So in a manufacturing process, if you have 2.5 nanometer thick silicon and you have plus or minus a few angstroms of variation across a wafer, that will lead to significant variations in the threshold voltage. And that's not really acceptable for, if you want to design a circuit to meet your power constraints or to meet your speed performance requirements. So ultimately, we knew that the thin body device couldn't be scaled. It's not going to be easy to scale that below 10 nanometer gate length. So the industry knew actually that, well, if we could actually make a double gate device, so have 2 gates, one on the top, one on the bottom, then we actually can get away with a thicker, we can still suppress leakage, but we don't need to have such a thin, physically thin body. Okay, so then if we want to scale the gate length to 10 nanometers or below, we actually can avoid going to body thicknesses much below 5 nanometers. Okay, so that's the idea of the double gate device. Now it turns out that in order for the double gate transistor to work well, the front and the back gates have to be perfectly aligned to each other, and they should be self-aligned to the source and drain to minimize capacitance and parasitic resistance. Now, and you need high performance. If you want high performance, this has to be a single crystalline silicon channel. So it's basically very difficult to form and pattern a gate electrode underneath the channel, and then form a single crystalline silicon channel over it, and then another gate electrode on top that's perfectly aligned. So basically a challenge, so let me show what happens then. As you thin down the body of this double gate device, so this is a contour plot of leakage current in the off state. So just comparing for the same gate length, what happens if you have a relatively thick body compared to a thinner body on the left? Red is bad, okay, or it's, this is an exponential scale. Okay, so red is like 7 orders of magnitude higher leakage current than blue. So you can see that you can actually suppress leakage very effectively by scaling down the thickness of the channel relative to the gate length. Now, in the 1999, we were looking at 25 nanometer gate length. So this is a simulation using Centaurus, which is actually what you're using for your design project. So we looked at the leakage current as a function of thickness, and we determined a basic rule that the body thickness really shouldn't be too much greater than about half of the gate length to suppress leakage. Okay, so the industry sort of recognized in principle that double gate MOSFETs are more scalable to shorter gate lengths. But the question is, okay, it's difficult to make a planar device. What if we actually made the silicon a vertical structure? So this is basically how we, so the option we decided to pursue is the FinFET, where you have the silicon defined in a vertical fin-like structure, like the back of a shark fin, I guess. And then we can actually have the gates on the sides. So this is the original idea then. And actually, there's researchers at Hitachi in Japan, the Central Research Lab, who actually first demonstrated a vertical double gate transistor. And the schematic illustration is shown here on the left. They actually fabricated it on a silicon substrate, and the silicon was patterned in a tall, narrow fin, and it was so narrow that they actually played some tricks, process tricks, to oxidize the silicon underneath the fin. That's how they got oxide all the way across here, just simply by oxidizing the silicon fin from underneath. Then they deposit a gate stack, gate oxide and gate electrode over that. So this was actually the very first vertical fin-like 3D transistor published, but notice, let's see, the gate length. What was the gate length? The gate length was pretty long. Where is that? Lower left. Oh, yeah, it's 0.57 microns. So nowhere, close to where we were aiming. So it turns out that Dai Hisamoto, he actually came to Berkeley in the late 1990s as a visiting researcher, and this happens a lot in our group. We have people visiting from the industry. So he came. Here are the measured current on a log scale versus gate voltage. So this is the subthreshold plot, just showing that as you scale down the thickness of that, or the width of the fin, you can get a steeper and steeper subthreshold swing. That means better gate control and so on. Okay, so he came to Berkeley, and he actually was the very first person to make a very nanometer scale vertical transistor. So what we did at Berkeley then was, just to summarize, we decided that the best way to make a double gate MOSFET is to turn the silicon, rotate the silicon on its edge. So what this width here now is that body thickness, right? So that body thickness has to be less than the gate length, no more than 2/3 or 1/2 the gate length. So this now the width of the fin has to be narrow enough, narrower than the gate length, okay, which is the separation between the source and drain. And then you have the gate electrodes straddling the silicon fin to control current flowing along the side walls of that fin between the source and drain regions. Okay? And the taller the fin, so you have current flowing on the side walls in the on state and in the off state. The taller the fin, essentially the wider your transistor is, okay, and the more current you can flow. So that's basically the difference between, okay, so here's the SOI FinFET. I'll pass it around just in case you have a hard time visualizing, but this is the conventional planar MOSFET if you want to compare. Right. So Intel actually put this into production, but let me say a few words about the work we've done to introduce it. So in 1998, that was the first FinFET published by Hisamoto, who was here. So the key thing is to note is now you can read these papers, right? You have the current on a log scale versus gate voltage. Okay, and that was for a gate length of 30 nanometers. Okay, so we didn't quite reach our goal of 25 nanometers in 1998. But see, the width of the silicon fin is 2/3 of a gate length. And notice, what am I showing here? This is a plot of the current for low drain voltage and for high drain voltage. So what does this shift represent? Dibble, right? Okay, so remember I mentioned dibble, no more than 100 millivolts per volt is actually what the industry requires. So yes, that dibble is less than 100 millivolts per volt of drain voltage applied. Okay, so we demonstrated we can actually suppress short channel effects pretty well, and the output characteristics look pretty well behaved. So notice, see, the spacing here is pretty equal as we increase the gate voltage by equal increments. So clearly this is a short channel effect. The current is limited by velocity saturation. So that next year, my PhD student published, that was N channel, we published a P channel device. Now the gate length now is below 20 nanometers. Okay, so that was the first FinFET PMOS and showed below 20 nanometers. But now look at the ratio of the width of the fin. So the width of the fin is 15 nanometers. The gate length was 18. So you notice the dibble is worse, right? Because the fin width is not narrow enough compared to the gate length. So qualitatively you can see. And so you see some slope, significant slope in the output characteristic, right? Again, due to dibble, all right? So we actually published some papers showing that if you want to have good dibble, we really don't want the fin width to be more than 2/3 of the gate length. So that's kind of the rule of thumb. But in manufacturing, you can get variations in fin width. So what the industry tries to do is optimally design it, the fin width to be 1/2 of the gate length. That way, if you have plus or minus some fin width in manufacturing, you still can get reasonably low dibble. Okay, so there's some interest in the industry, so we ended up filing a basic patent that actually has been licensed to some companies already. So as I mentioned, the goal was to reach 25 nanometers. So at that time, we started to transfer this technology to the industry. We did additional work here at Berkeley, but we started to transfer this. So Professor Hu went to the leading foundry, TSMC, from the years 2000 to 2003 to transfer this technology to TSMC, which might introduce FinFET technology next year. I stayed here at Berkeley. We were continuing to push scaling of the FinFETs. So we went down to 15 nanometers, and this, so notice on this slide we published in 2001. So both N-channel and P-channel with reasonable dibble now at 15 nanometers. And interestingly, I'll mention this. Okay, I'll ask. Notice the NMOS and PMOS current, output current characteristics. Okay, this is the magnitude of current, right? Otherwise PMOS would be negative. Ordinarily, from, let's say, people who take EE131 and so on, what is typically the ratio of the N-channel MOSFET current to the P-channel MOSFET current? 3 or 2 to 1, right? So, and usually the electron mobility, field effective mobility, is at least 2 times higher than the whole field effect mobility. But notice here, the ratio is not really, for the same amount of gate overdrive, gate voltage minus VT, you don't see that much difference between the NMOS and PMOS. And actually, indeed, in Intel's 3D transistor CMOS technology, the P-channel devices have pretty much just as much on-state current as the NMOS devices. The answer is later on, but can anybody explain why? Now, these are the same dimensions. Squish. Oh, the stress, that's true. So Intel puts strain in the channel region, and the strain actually benefits the PMOS more than the NMOS devices. That helps compensate. Remember your very first homework assignment? Different crystalline orientations. So I think that's, let me skip to that for now. Yeah. So if you actually have silicon etched as a fin, the sidewall surface orientation is different. Right? The normal silicon wafer surface is 100. The sidewalls, if you orient the transistor like in a normal layout, the sidewalls will be 110. So you remember which plane is the best for hole mobility? 110, right? But that's actually not good for for electrons. So basically, if you go to 110 surfaces, sidewall surfaces for current conduction, you're actually sort of degrading the N-channel performance, but you're greatly enhancing the P-channel performance. So overall, your CMOS performance actually improves. Okay, but that's the main reason why the current is actually more balanced. For exactly the same transistor channel dimensions, the NMOS and PMOS currents are actually pretty comparable for FinFETs. Okay? All right, so let's go back. So in 2002, we actually transferred the FinFET technology to AMD, which used to have a fab. Okay, so today they spun off Global Foundries. But we showed that the FinFETs could be going down to 10 nanometer gate length. And the interesting thing about this work is that all of this work was done in AMD's fab. Okay, so in other words, it was a conventional CMOS fab. We didn't need, this proved that we didn't need any fancy new materials or processes to make these devices. And that's one reason why the industry ultimately was able to implement this in manufacturing, right? Nothing really too new in terms of process requirements were needed. They just needed to be able to pattern a feature, the fin, to be smaller than the gate length. Okay, that's the big challenge. Okay, so Intel, let's see, in 2003, published its first 3D transistor paper. Notice the gate length is 60 nanometers, so nothing really close to what we had proven was possible. But nevertheless, the width of the fin, not too narrow. They were able to suppress the dibble and get pretty reasonable performance at the first try. Now, Intel called this, okay. So one reason why they were able to get away with a kind of a wide fin, okay, not that much narrower than the gate length, is because that fin was also short. Okay, so that's why they call it a tri-gate transistor. They actually had the gate, well, of course, on the sidewalls, but also the gate on the top And this silicon was actually rather thin, so it's kind of like in between a thin body transistor and a double gate transistor, right? So the fact that they made the silicon relatively thin as well, right? It's thinner than the thickness of that silicon fin. It's not really a fin anymore. But anyway, the thickness, the height of that fin is less than the gate length. So there's actually a thin body device and a double gate, on the side. So it's 3 gates. That's why they call it a tri-gate device. And because a lot of the current is conducted on this top surface, then you don't see that huge, benefit on the PMOS, right? The PMOS current is certainly still much less than the NMOS current, because this just sort of proves that most of the current is flowing on the top surface, not on the sides. Okay, so after that, so that was on a SOI, silicon on wafer, silicon on insulator substrate. So here's a cross-sectional view of the fin in the lower left corner, and you have the buried silicon dioxide underneath. Now, Samsung was the first to demonstrate that you can actually make a FinFET with just a conventional planar bulk, with a conventional bulk silicon wafer. So that could save a lot of cost, because the cost of making an SOI substrate is pretty high. So on the lower, on the left, sort of illustrates schematically the fabrication process. So in a CMOS process, you first define the regions where you're going to make the transistors. So that's here. And it turns out, okay, and then you usually fill, so you etch down the silicon and fill the regions in between the transistor regions with oxide. So it's insulating, right? This is the shallow trench isolation oxide that we talked about. But to make FinFETs, all you have to do, well, it's not trivial, is to define your silicon transistor regions to be very narrow. Okay, so if you define your silicon transistor regions to be very narrow, and then you have one extra step with a mask. Okay, so you have a mask to only allow etching of the STI, the shallow trench isolation oxide. Here, where you want to more form FinFETs, you can have a masked etch or recess etch of the silicon dioxide shallow trench isolation to expose the sidewalls of the fins. So that's the only, in principle, the only extra step you need to form a FinFET. So now you've exposed the sidewalls, and then when you form the gate oxide and the gate electrode, the gate electrode will naturally straddle the narrow, tall fins, and it'll naturally be flat, planar across the unrecessed areas. Okay, so you can, in principle, you can make planar bulk MOSFETs side by side with a bulk FinFET. Okay, so there are a couple of things here that are a little tricky. First of all, the whole reason of using an SOI is to prevent leakage. Okay, so in the model is passing around. If you have a FinFET and you have a gate, if there's silicon, if it's a bulk silicon wafer, then you actually can have leakage between the source and drain regions underneath the gate electrode, right? Because so basically what they need is this. Oh, I forgot to put here. So you need doping. Shoot. Okay. Let me just draw it. So you have in the cross section you have a fin. Okay, and let's say we have recessed silicon dioxide, shallow trench silicon dioxide, and then you have a gate that straddles the fin on the top and both sides. Okay, so you have current flowing along in the fin under the control of the gate, and you have source and drain regions on either side of this gate. But you actually can have leakage in this region down here, right, between the source and drain regions, flowing down beneath the control of the gate. So basically what you need is you need some heavy doping. Like for an N-channel device, you'd make that heavily P-type at the base of the fin to prevent leakage between the source and drain that's out of control of the gate. So you need some retrograde doping at the base of the fin if you use silicon, bulk silicon, as the starting substrate. So that retrograde doping step is not trivial to get very, very steep, suddenly increasing doping beneath the gate. Okay, so you need that. Also, if you have a tall fin, if you want to form the source and drain regions of that fin, you have to dope. You have to implant your source and drain dopants pretty deep, right, from the top of the fin to the bottom of the fin. Okay, so usually the height of the fin is going to be deeper, or deeper than, let's say, the source drain extensions of the planar bulk MOSFET. Okay, so basically, you need different doping steps, not only for the channel region to form this, what they call a channel stop implant at the base of the fin, but you also need different source strain implants, right? Because the source strain implants for the planar device must be shallow to suppress short channel effects. The source and drain implants for the fin have to reach down to the base of the fin. So if their fin is tall, then you need pretty deep source strain implants. So it's not trivial to have planar CMOS devices manufactured side by side with FinFETs. And actually, that's the reason why the foundries or Intel, basically, if you look at their 3D transistor chip, every transistor on their chip is a 3D transistor. It's not like you can select some to be 3D and the others to be planar. All of them have to be 3D because the fabrication process is too complicated otherwise. Russ? The question is, why would you want to mix the two? Okay, well, so this is one reason why it's taken a little while for the FinFET to be widely adopted. So one challenge with the FinFET is how do you, usually if in a circuit design, you would like to have some transistors conducting a lot of current, some not. So in a memory cell, you might want to have the smallest transistor because it doesn't need to conduct that much current, but you want to save area to fit more memory into a certain chip. Other parts of the circuit, you want to operate faster, so you want them to be wider transistors to conduct more current, to charge and discharge capacitors more quickly. Now, normally the circuit designer can draw a wide channel region. Right here, you can make the channel region really wide to conduct a lot of current. Now, for a FinFET, how do you do that? How do you make a FinFET wider? You can make it taller. That makes it harder to manufacture because you have this narrow thing, and you have to etch vertical sidewalls, and it's going to be a huge aspect ratio. So the way to do it is actually you still draw a wider active area, the transistor area, but you have multiple fins. Now, from a circuit modeling, circuit designers need to be able to accurately predict transistor performance. And so the modeling of how the FinFET current increases with the number of fins is actually kind of tricky because actually if you have multiple fins in parallel, actually the outer fins are narrower than the inner fins, and so it's not trivial. And then also, if you want to increase the current flowing in a FinFET, you have to increase it by increasing the number of fins. So that means it's quantized. You have to increase it in like steps, and so that's not trivial. So for analog circuit applications where you want to fine-tune the ratio of transistor strengths and so on, it's not that trivial. So actually, a planar bulk device would be just fine for analog. Because in an analog circuit, you never turn off the transistor, right? You just keep it on and you just modulate how strongly it's on. So maybe for analog and some other like RF applications, actually planar bulk MOSFETs are just fine and actually perform better than the FinFET. But in any case, if you go with a FinFET technology, all of the transistors on chip have to be FinFET. Otherwise, the fabrication process is kind of too complicated. Now, Peter, you had a question? Okay. Yeah, so that's something that's not really heavily advertised by companies, right? They like to say all the good things. All right, so as I mentioned last time, the industry, before they introduced the FinFET, right, the FinFET was introduced only this decade. In the last decade, what has the industry done? It's introduced strained silicon, and it's introduced high-K metal gate. So of course, we had to show that the FinFET was compatible with high-K metal gate materials, and indeed, we demonstrated molybdenum as a gate material and hafnium dioxide as a high permittivity gate dielectric for NMOS and PMOS devices, and showed, so here are the measured current versus voltage characteristics. So these are the transfer characteristics on the left, output characteristics on the right. Now, if you look closely, there's something kind of not perfectly right here. Can somebody mention? It's not symmetric, right? So, actually, we tried. So the point of this paper was actually we could implant a little bit of nitrogen into the molybdenum gate to tune the gate Worf function to try to get it to be symmetrical. So even though this doesn't look symmetrical, it was more symmetrical than what everybody else had published to date. Okay, so that's a fundamental challenge actually today. How do you adjust the threshold voltage of a 3D transistor? I mean, how do we do it for a conventional transistor? Ion implantation in the channel. Now, ideally, though, for a FinFET, we don't want to implant any dopants in the channel. And I guess I can explain that why. But just take that for now. We don't want to. We cannot really easily adjust the threshold voltage by changing the doping in the fin. So how else can we tune the threshold voltage? Bias. Oh, there is no body bias in a FinFET. That's a good question, right? If you think about it. There is no body bias because in a normal transistor, you can grab the back side of the body, right? You can bias that. But in a FinFET, you actually have both sides connected to the gate, so you have no body to grab. And actually, that provides for the best gate control. So basically, if the gate voltage is changing, you're changing the channel potential perfectly. So you actually, in principle, can get 60 millivolts per decade. If the drain doesn't, if the drain capacitance is not significant, you can get 60 millivolts per decade slope for a FinFET. And actually, in some of these devices, pretty close, as you see here, close to 60 millivolts per decade. Right? So if you get steeper subthreshold swing from the homework assignment, was that due already? Okay. You can get better on-off current ratio, right? Okay. So yeah, so the gate work function tuning. So Intel does have slightly different metal materials at the oxide interface for N-channel versus P-channel devices. So that's how they tune the threshold voltage. Actually, they also implant it. Okay, so another way that people have explored for tuning the threshold voltage is to take advantage of the VT roll-off phenomenon. So if you, I should get a better pen. So if you plot the threshold voltage, you still get a little bit of short channel effect. Threshold voltage versus gate length, you'll get some variation. So actually, on Intel's chips, they do actually have different gate lengths. So different gate lengths give you different VTs. So you can tune the trade-off between performance and power consumption this way. OK, so a very simple question is, why wouldn't we want to dope the fin to tune the threshold voltage? It decreases mobility, that's true. But there's actually a more fundamental question. So I need, OK, let's see if I can do. OK, maybe it would be a good exercise. Yes, James. It's more difficult because you have a vertical structure. Well, it turns out that you can implant the dopants into the fin and do some thermal annealing to diffuse it to be pretty uniform. It turns out that if you look at the volume, OK, so this might be a good exercise. Look at the volume of the channel of a FinFET. OK, so let's do a little exercise here. OK, so let's say the depletion. OK, let's just look at the volume of channel region. OK, I'm just going to exaggerate here. So let's say it's a 10 nanometer wide fin. And let's say the fin height is, I'll just say it's 100 nanometers, although that aspect ratio, 10 to 1, is actually kind of hard to manufacture. And let's say the channel length is 10 nanometers. Okay, so how many square centimeters is that? I mean, cubic centimeters is that? It's 10 to the minus 6 times 10 to the minus 5 times 10 to the minus 6. So it's 10 to the minus 17, right? 10 to the minus 17 cubic centimeters. OK, typically how much dopant, what's the dopant concentration in the channel like for some reasonable threshold voltage? 18, 10 to the 18. So how many dopant atoms are there going to be in a fin channel? 10, less than 100. OK, so in the manufacturing process, from one FinFET to another, it's very likely, there's a central limit theorem. So the variability, basically percentage-wise, if you go from one FinFET to another, and let's say you have a change in like a few atoms more in one fin versus a few atoms more in another fin, that's going to lead to significant variation in the threshold voltage, right? So simply because the volume is so small. So you cannot reliably dope the FinFET and precisely control the number of dopants to precisely control the dopant concentration that determines the threshold voltage. So VT variation actually gets much worse in a FinFET if you try to dope it to control the threshold voltage. Okay? Now, if you dope it really, really heavily, like in the source and drain regions, simply to get conduction, it's OK. But just fundamentally for the FinFET, it is not a good idea to dope it, to tune the threshold voltage by doping, simply because that will result in too much variability. Okay, so sigma VT, you know, the standard deviation of variation actually can be pretty high once you scale the FinFET down. So that's not ideal. So as I mentioned, Intel, you know, basically announced in 2011 the FinFET. Notice they decided to use the SOI, not an SOI, but silicon substrate because it's lower cost for manufacturing. But this means that, so this is the fin width here, and here's the fin height, right, that determines the transistor width. But notice they have to etch more deeply, maybe 50 nanometers or so more deeply to form the isolation oxide, you know, the oxide that isolates one transistor from another. And then in the silicon, to prevent leakage from flowing between the source and drain through this silicon fin here, they have to dope the fin very heavily, you know, underneath here. Okay. All right, so these are cross-sectional micrographs of their FinFET. So people were actually surprised when they first looked at this. It's like not vertical sidewalls, it's sloped, okay? And you know, the gate wraps around like that. But this is a cross-section through the source and drain region of a P-channel MOSFET. So this, they grew the silicon, remember the silicon germanium that's grown to induce strain in the PMOS devices? They grew the silicon germanium on top of silicon in the source drain fin regions. Okay, so in production, it's about 30 nanometer gate length, and the width of the fin at the top is only 8 nanometers. Pretty small, yes? Okay, so the question is, why is it, essentially, why is it a triangular fin? So that's a good question, and Intel says that it did this for reliability issues. Basically, you know, first of all, if you make the corners too sharp, when you turn on the transistor, electric field is concentrated in the corners. So basically, you know, to avoid these super high electric fields right in the corners, they had to round the corners. So they found that a radius of curvature of about 4 nanometers was best for reliability. If you have high electric field, vertical electric field here in the corners, that can cause electrons or holes to go into the gate oxide, you know, charge trapping over time, and BT shifts over time, and eventually breakdown of the dielectric in the corners. So they said it was due to reliability. Now remember, I don't know if I mentioned that Intel forms this high K metal gate stack last. Okay, so what they do is they actually first form a polysilicon gate and then use the polysilicon gate to mask the source drain implants. Right, so you have perfectly aligned source drain junctions with the gate. Then they remove the polysilicon gate and replace it with metal, the high K metal. And so, you know, etching away a material along the sidewalls is not easy, and then conformally depositing material along the sidewalls, if they're perfectly vertical, it's not easy. So sloping the sidewalls actually helps, right, with the conformal removal of the dummy gate and deposition of a conformal gate stack. Also, if you implant the dopants, source drain dopants in the source drain regions, it actually turns out to be hard to dope the fins, somebody did mention. So if you slope the sidewalls, you can actually get more dopants into the fin. But it turns out then that Intel heavily dopes its fins near the bottom here, right? So for an NMOS device, they dope it P+. So it's not from an ideal perspective, this is not the best geometry to maximize your FinFET performance, but that's what they had to do to get a manufacturable process. So notice the current versus gate voltage characteristics, pretty nice and low subthreshold swing and low dibble. Okay, so you should recognize that, you know, dibble less than 100 millivolts per volt is good for such a short gate length device. Subthreshold swing is pretty good. And compared to a 30 nanometer generation of technology, for the same off-state leakage current, they could boost their on-state current. So in other words, you can enhance performance for the same kind of leakage, or you can actually go to lower leakage for the same performance. Okay? Okay, so what's beyond that? Well, we know that there's going to be some scaling limit for transistors. And so we have research. So today we are looking at the future transistors. So I told you it took 12 years, right? We did that FinFET work in the last century. So that's last millennium. So that's like late 1990s. So today we're working on things that we think the industry will need more than 10 years from now. So today we're working on transistor designs that can operate not only, you know, well below 1 volt. So the FinFET, people project you can go down to half a volt. So you can reduce the power supply voltage by a factor of 2, so you can lower power, active power consumption by a factor of 4. Today we're looking at research trying to go down to millivolts operation to save a lot more power. Okay, so if you're interested in that, I can tell you about that. But in any case, eventually we're not going to be able to scale, miniaturize the transistors any further, and we're going to have to continue to do device research, but more coming up with novel transistor designs, maybe incorporating novel materials. This is what we call heterogeneous integration. The key is that we still have plenty of room for innovation to lower the cost. Remember, that's Moore's law, right? The whole point of Moore's law is to lower cost per function. And we can actually improve energy efficiency with these novel transistor designs. So this virtuous cycle that we started out with at the beginning of this course will continue. It's just that maybe in another 15 years or so, it won't continue due to transistor scaling, but it will continue due to other means. So that will enable us to have thousands of devices per person, trillions of devices rather than billions of devices that are not going to consume all the energy, electricity in the world. But so energy efficiency is really going to be the key technology driver for future transistor development to enable us to have trillions of electronic devices embedded in us, in our world in the future. And that's the vision we have for our device research, is to allow information technology to continue to proliferate so they'll become pervasive, embedded in us, in our environment, and hopefully continue to solve some of the world's biggest challenges. Okay? And that's it. All right, so next time we'll go back to another transistor design, BJTs. Okay? So the social hour today will be indoors because of the rain.